So yeah, so first part of the fundamental theorem tells us how to actually compute integrals. Second part tells us how to solve differential equations. And those things are hugely important in all of the applications that you've seen and everything. For those, cover a great deal of ground in the real world. So that's why it's a fundamental theorem of calculus. A lot of what we did in calculus rests on that. Stuff you did just with plane derivatives, not as much, but that's okay, it can't be everything. So that's our fundamental theorem. When we look at integration, and this is actually true of any process that we define on functions, differentiation as well, two big questions. One is, what functions can you do this to? Jacob, would you check and make sure that's... Let's see. What functions can you actually apply that process to? And then the other one are, what properties does the process actually have? What?
So this fundamental theorem in calculus strictly talks about Riemann integrable functions, even though we don't necessarily know any other kind right now.
Well, everything in your proof used the definition of a
Riemann
integral.
Okay.
So if you come up with a different definition for the integral, you would have to redo this proof. And if you go on in analysis and you go take graduate analysis, you'll get the definition of the Lebesgue integral, and then you'll redo the proof for Lebesgue integration.
And it will be fundamental again?
Oh yeah, it's still the fundamental theorem of calculus.
Oh, okay.
So the fundamental theorem of calculus, if you write it down, it always says exactly the same thing. But hidden behind it is, well, what definition of the integral are you using?
Well, also,
bizarrely, there's also different definitions for the derivative.
Oh.
And so you can actually switch up the definitions of the derivative of the integral and then ask, well, does it still work?
there's a whole bunch of other types of, so this is like called Newtonian Newtonian calculus, and there's other types of calculuses, right?
Oh yeah.
Because they handle different, they start with a different definition of integral and derivative.
Or you do them on different kinds of sets. There's an interesting book in the library that shows how you connect doing it discretely. So instead of integrals, you have sums. Instead of derivatives, you have averages. And so you have that. And then over here, you have usual definitions in calculus of integral and derivative. And then how do you bridge the gap between what happens when it's discrete, when you do it in jumps, and when you're continuous and you can subdivide anything, you can take limits. And it's fascinating, has some interesting topology in it. But yeah, there are, I mean, I haven't even studied all the different kinds of calculus. But. All right, so we have that. And this is going to be true of any process. And so we've been dealing actually with both questions. And we've been talking about, well, you know, what's integrable? And then what do we know so far about what functions are Riemann integrable?
Well, they have finite discontinuities.
Okay. So,
Although I suspect from reading the book that we can change that without changing the definition of the integral.
So we actually have a proof, you did the proof, that if it has a finite number of discontinuities, then it's Riemann integral. Bounded function. So if we're really putting this out here, it has to be bounded
Would you say it's on a compact set?
on a closed bounded interval. So that's what we have so far, though both of those turn out to be too restrictive. As you know from calculus, you did integrals over unbounded intervals. And as we'll see, you can do it, it did an example in the book, but you can have countable number of discontinuities, you can actually have an uncountable number of discontinuities. And still be Riemann integral. And so, yeah, where we're headed next time is to fill this all the way in. We're actually going to do the doctoral thesis of Henri Lebesgue. Well, okay, not the whole thing, but the main part of it.
Which is what?
Which is to say that a function is Riemann integrable if and only if its set of discontinuities has measure 0.
So over the, so like we could do it over where there's discontinuities over the Cantor set.
Yes.
That could be useful.
Tomei's function is discontinuous on rationals. And so it's discontinuous at every rational number. But turns out it's still Riemann integral.
It comes out to 0.
Because the rationals are a set of measure 0. Alright, so we're going to go make sense out of that, but that's what we've seen so far, and it's always a big question anytime you define a new process. Well, what does this process actually work on? And then the other one is properties, and when we talk about properties, what we're really looking at are how does this process interact with other processes. So, I mean, if you look at the properties they did, we say, well, how does it interact with addition?
It's homomorphic.
So,
That's
that's
a
a
linear
question.
operator.
You have to define what spaces you're talking about.
Yeah.
You have two integrable functions, you add them together. Is their sum still integrable? And if you take the integral of the sum, how does that relate to the integral of each one individually? And so you look at arithmetic down here and say, how does it interact with arithmetic? You look at, as you will in some of the homework problems, how does it interact with limit processes? So you've got sequence of functions, and their limit is another function. Well, if all of the functions in the sequence are integrable, and if the, is the thing that they converge to integrable, and so forth and so on. So both are very important questions. Some, they're different, but that's what we're looking for is in this whole chapter is to try and kind of round that out, get a feel for all of it. So as you look at that, questions, areas of concern. None? Then we'll see when it's going to work.
Let's see here.
What we're going to do on Wednesday is get the ultimate answer to that one. To do that, we have to introduce the idea of measure. Now, this is not a measure theory class. We are certainly not going to define measure in all of its glory.
Oh.
But we do need to know what it means to be a set of measure 0.
Doesn't it mean it's just countable?
No.
No?
No, because we just talked about uncountable discontinuities, but still with measure 0.
Yeah, it's certainly true that any countable set has measure 0.
Okay.
But the other way is not true. There are lots of
Not.
sets that have measure 0 that are not countable. So what does it mean? So what we're trying to do here is measure how big a set is. And if you think about when have you actually measured the size of sets, what's the only set really that you know how to measure?
Real numbers.
Well, the real numbers would be super infinite, but subsets of the real numbers. What subsets of the real numbers can you confidently tell me I know how to measure that set?
Integers.
No.
No.
Interval from 0 to 1.
Intervals.
Because measure doesn't have a really close connection with length.
Well, that's the whole idea. Is if we're in R1, then we're trying to define the length of this thing. If we're in R2, we're trying to define area. If we're in R3, we're trying to define volume, and so forth.
But
and so on.
beyond that,
Beyond that, then we still call them volumes, hypervolumes if you want to be ticky. But basically, an interval is what we really know how to measure, what we think we have a really good concept of measure about. And if we are, going from A to B, then we talk about the length, which for us is going to be
B minus A.
the measure.
Oh.
And that's just the absolute value of B minus A. I mean, you actually need the absolute values in that particular case. But
So the interval from 0 to 1 has the measure 1.
yes.
So
Well, now I should be careful. Just like anything, you can define different measures. And so in different measures, it might have different lengths.
so wait a second.
Let's not jump there yet. All we're saying
Wait a
is
second.
we feel like we know this. We've done it a lot. It makes sense to us. Everything's good. So if we're going to define a general sense of measure, we're going to start back here with what we think we understand. And so the real numbers, it's hard to claim you know anything. But so a set of measures 0. So we have some really funky, set. It's got some Cantor sets in it. It's got, what else in there. But some subset of the real numbers. We allow for pretty much any subset, although, as you find out, it turns out that the real numbers are so bizarre that you can basically construct sets that, under any sense of what length is, you have no idea what the length is.
What?
Unmeasurable sets. And defining them is weird, but anyway. So a set of measures 0, all we would care about is measure 0. And we're going to say that we have a set of measures 0. We're going to go back to intervals again. And basically what we want to do is we want to cover this up with a bunch of open intervals.
Open covers.
So we want all of the points in our set to be inside these open intervals.
Oh.
So we have
Do we
an
say
open cover
measure 0
of our set.
So we have an open cover of our set, if you know. Did you guys do it?
461.
Yeah.
461, yeah. So you have an open cover of your set. And then we know how to define the length of each of these open sets. It's just the one endpoint, it's the upper endpoint minus the lower endpoint. And we can add up the lengths of all of those open sets. And so to be a set of measure 0 means that you can find some open cover where the sum of the lengths of all of the sets in your open cover comes out to be less than epsilon for any epsilon. So basically, what we say is that for all epsilon greater than 0, you can find an open cover so and we are going to require it to be countable. So that our set, whatever S is our set, is contained in the union of each of these open sets, and the sum of their lengths is less than epsilon. This is the length.
For every
The nth open set.
That's weird.
So basically, you cover it with open sets such that the sum of the lengths of the open sets goes to 0. It's arbitrarily small.
Oh, that makes sense.
So what might be an example of an uncountable set S?
With measure 0.
With measure 0.
Counter set.
List the uncountable sets you know.
Counter set.
The Cantor set. Cantor
The real
set
numbers?
has measure 0.
The real numbers?
We have measure real number.
The real numbers do not have measure 0.
The irrational numbers?
The irrational numbers do not have measure 0.
Do not?
No.
That's because
Rationals
you have to
are
combine uncountable with countable when you
Well,
combine.
just take the interval from 0 to 1. It's made up of rational numbers and irrational numbers.
Uncountable
And
unit.
we can prove that any countable set has measure 0, so the rationals would have to be 0, or measure 0.
Yet the
Yeah, the whole interval has
one-
measure
1.
1. So the irrationals in the interval from 0 to 1 must have measure 1. Now, we're not going to talk about how you actually get, overall measure for a set. We're just defining what it means to be a set of measures 0. Turns out that defining measuring in real generality gets extremely abstract and introduces some topological complications that we just don't want to get into. I'm talking about sigma algebras of sets. So, fun stuff, but it would take us the rest of the semester to
You could just turn this into a topology course, right?
measure theory. Actually, you can get books on measure theory.
You can hit yourself over the head with a book about measure theory.
It's fun.
Does it have applications?
Huh?
Measure theory? Does it have
To probability.
applications?
Yeah. For instance, when you say that something has probability 1,
What, measure 1?
there may be uncountably many instances in which the thing doesn't happen. But the set of values for which it doesn't happen has measure 0.
Oh.
But that means that whatever you're defining may not happen on any of the values in the Cantor set. But you still say it has probability 1. So it gives you a whole new idea of what it means to be probability. Probability 1 doesn't mean that it always happens. It may not happen on an uncountable set. But that set is small.
So
In some
small,
sense.
we can call it
Wow.
0.
Great.
Yeah.
The ratio.
So that's why what you end up doing when you get into probability theories, you say that it happens almost always,
Yeah.
which means that it doesn't happen on a set of 0, set of measure 0. You talk about properties that are almost everywhere. And then what really gets fun is that when you talk about functions, you're no longer talking about a function, you're actually talking about equivalence classes of functions. And two functions are defined to be the same function if they differ on a set of measure 0. So they're not the same pointwise.
So for instance, a function with a single discontinuity is equal to the same function.
Is equal to exactly the same function.
Okay.
So, yeah, anyway, lots of fun stuff that goes on out of this. But for us, all that matters is that we understand what it means to be a set of measure 0. And now what we're going to prove is that every function whose discontinuities are a set of measure 0 is Riemann integral. So, 7.6, Wednesday. You will notice that it basically has a sequence of exercises as you go through the reading. And so what we will do on Wednesday is start working our way through those exercises to prove the Lebesgue theorem, which is that the Riemann integral works on any